So one more video to talk about a clinical connection for pyrimidine biosynthesis. In a previous video on page 114 here, we talked about how we convert UTP to CTP. That was a classic nitrogen ligase, great chemical mechanism, but we're going to put that aside now. I'd like to move on and talk about how we convert UTP into DTTP, that is 2'-deoxythymidine triphosphate. This is our last real nucleotide that's needed in the pyrimidine arena, and this would be needed for DNA. Let me make a big point here, and that is that anytime we are making nucleotides, we have the ability to knock out cell proliferation if we can inhibit these pathways. And so making DTTP is critical for any cell that is growing, including cancer cells. So I've got a couple of enzymes here. We're not going to talk about their mechanism, but I do want to address their importance in the world of medicine. The first one is called ribonucleotide reductase. And as its name suggests, it does a reduction reaction, and something needs to be oxidized to do that. What we're going to use, as we have many times, is an NADPH, emptying its hydride ion out to be an NADP+. When we synthesize things and we need electrons, we use NADPH typically as a hydride ion donor. So, where do those electrons end up? They end up right here between carbon number 2' of the ribose and the H that's now attached there, in place of the 2' hydroxyl, which is lost. So what do we need to know about this? Not much. I just want you to know that this is a complex reaction. It uses a radical intermediate. If you're interested, the book goes through it in a lot of detail, but we're not going to do the mechanism. What I am interested in telling you is the product name. It's 2'-deoxyuridine 5' triphosphate, or DUTP. Now, mind you, that molecule is not really of any use in the body because deoxynucleotides are for DNA and uracil is used in RNA. However, we are going to take DUTP and make it DTTP, so that's coming up next. I also want to point out that in order to get to DTTP, you must go through this step. And because of that, this ribonucleotide reductase is a target for chemotherapy. And for example, let's take a look at this molecule down here. This is called gemcitabine. And what it is basically a cytidine type nucleotide, except instead of a normal 2' hydroxyl with an OH hanging off there, it has a fluoro group and another fluoro group. And this is an inhibitor of ribonucleotide reductase. It's going to get into the active site, and those fluorine groups are very active and are able to mess up the radical type reaction that's going to be happening. So this is a terrific chemotherapy. It is used for a number of cancers, including breast cancer, pancreatic cancer, and bladder cancer in particular. Now, mind you, chemotherapies that target pyrimidine synthesis or any nucleotide synthesis are highly toxic. The reason for that is because it's not just cancer cells that need pyrimidines, it's a lot of other cells. And because of that, we can start to lose blood cells, and we can start killing off our own regular cells in addition to the cancerous cells. So it's a matter of dosing it in high enough to hit the cancer cells, but not so high that we do a lot of toxicity. So that's gemcitabine and ribonucleotide reductase. Let's move on to the other side over here and talk about another really interesting enzyme. This one is called thymidylate synthase. Thymidylate synthase. And what I would have you do is take a look at the substrate DUTP and the product DTTP, and what we see is we're going to be doing a methylation. That's the only difference between T and U, and again, this is a very complex reaction, but I do want to point out that there is a connection to something we've talked about in the past in a previous video, and that is this is using a one carbon transfer, and that means THF. So up here we have a slightly different version of THF methylene. Let's go ahead and write this down here. THF methylene. That is going to donate that group to uracil to make thymidine, and we empty out the THF. When we've transferred that carbon, you just have those two empty N5 and N10 nitrogens up there. Now, the interesting part of this is that in order to do this reaction again, naturally we have to take the THF and fill it up with another methylene group. So, interestingly, there is a recycling enzyme that fills up the THF again with a one carbon unit, and the enzyme that does that can be inhibited by a compound called methotrexate. And methotrexate is another very famous, got to spell it right, methotrexate. It's another famous chemotherapy, very toxic, but also able to knock down this process. And if you don't get DTTP, you cannot proliferate, even for cancer cells. Finally, at the bottom of the page, we see a third chemotherapy agent, and this is called fluorouracil. Very famous, one of the original chemotherapies. I think it was first invented in the 1950s, and all we know about this is that this inhibits thymidylate synthase as well, and the process of making DTTP. So that's enough just to make some connections between this anabolic process where we're making nucleotides and very important cancer chemotherapy.